Quantum doesn't fail because the math is too hard. Quantum fails because the hardware turns into a cryogenic spaghetti monster the second you try to scale it. And that's why photonic quantum sounds like a cheat code. Because the pitch is basically, stop fighting wires and refrigerators, put qubits on chips, route information as light, scale with manufacturing. In other words, turn quantum into something a foundry can ship. Now, before anyone gets emotionally attached to laser beams saving the world, here's the reality filter for this episode. Photonic quantum might be the cleanest scaling story in the field, or it might be the most expensive way to discover that physics charges a toll for everything. The make or break question is simple. Does optical loss and error correction overhead eat the advantage before it becomes useful? Because photonic doesn't mean free. It just means the villain wears a different costume. And today, we're doing a scoreboard episode. Not who's winning, not who raised money, not who has the prettiest demo, just the test. What has to be true for photonic quantum chips to actually win on reality? Chapter 1: Quantum's Silicon Crisis. Let's ground this in the real bottleneck. Scaling quantum hardware is less like building a faster computer and more like trying to manufacture a violin where every atom has to stay in tune while a tornado screams in the background. You need wiring, control electronics, packaging, thermal management, stable timing, clean signals, good yields, and systems that can run for long periods without turning into a science project. That's what I mean by a silicon crisis. Not that silicon is failing. It's that quantum wants silicon-style scaling, but keeps getting dragged back into lab rig reality. Now enter silicon photonics. Silicon photonics is basically chips that route information as light through tiny waveguides using manufacturing methods that look a lot like the normal semiconductor world. And silicon photonics is booming right now for a totally non-quantum reason. AI data centers are starving for bandwidth and energy efficiency, and optical interconnects are one way to feed the beast without lighting the building on fire. That matters because it creates industrial gravity. When an entire industry is investing in photonic packaging, alignment, testing, and manufacturing throughput, quantum photonics can potentially ride that wave. And this is the core photonic quantum thesis. If we can build quantum-grade photonic components on chips, we can scale the plumbing of quantum the way we scale normal compute infrastructure. But the phrase quantum grade is doing a lot of heavy lifting. Quantum photonics needs more than waveguides. It needs single-photon sources that behave, circuits that stay stable, switching and fast feed-forward control, and detectors that catch photons without adding chaos. So the first filter is brutal and boring. Show me the end-to-end stack, not the vibes. Because the web of constraints is where quantum dreams go to become grant proposals. Chapter 2: The Photonics Scaling Thesis. Now the photonics scaling thesis, stated cleanly. Photonic qubits encode quantum information in properties of photons, and photons are naturally good at traveling through optical systems. They don't have the same wiring density problem as everything must be an electrical line into a fridge, and they're naturally compatible with fiber, which is basically the global nervous system already installed. And some photonic roadmaps lean into a model called measurement-based quantum computing. The idea is you generate a large entangled resource state, sometimes called a cluster state, and then you compute by measuring parts of it in a controlled way. Think of it like building a huge quantum scaffold, then carving computation out of it with measurements. The reason companies like PsiQuantum get so much attention is that they frame their plan in manufacturing terms, not "we will hand-build a delicate miracle," more like photonic qubits plus high-volume semiconductor manufacturing aimed at fault tolerance. That's an unusually concrete posture in quantum, where it's easy to hide behind impressive demos that don't actually upgrade into reliable machines. But here's the catch, and it's the whole episode. Manufacturing leverage only matters if the physics layer is good enough. If your components are too lossy, too noisy, too probabilistic, or too hard to stabilize, then scaling just gives you bigger piles of the same problem. So the honest debate is this: does foundry leverage beat physics overhead? Photonic quantum is the bold attempt to answer yes. Skeptic mode answers, show me the loss budgets. Because if you can't write down the loss budget, you don't have a plan. You have a mood board. Chapter 3: The Loss Tax and the Overhead Bill. All right, the villain reveal. In photonics, the existential enemy is photon loss. Loss is a tax you pay every time light moves through a real system. Sources, couplers, waveguides, splitters, switches, chip-to-fiber connections, and detectors. Every little loss feels small until you multiply it across a huge architecture. And quantum is not forgiving about this, because you're not moving signals, you're moving fragile quantum states. So if someone says photonics scales, the immediate follow-up is, scales to what exactly? Because loss doesn't just reduce performance, it changes the economics of error correction. Here's the clean version of why. Error correction is how you turn unreliable physical hardware into reliable logical qubits. But error correction only works efficiently if the physical error rates and losses are below certain thresholds, and if operations are repeatable enough that overhead doesn't explode. If the physical layer is mediocre, error correction becomes a debt spiral. You can keep paying overhead forever and never become useful. That's why advantage demos can be misleading. A demo can be impressive scientifically and still not meaningfully reduce the distance to fault tolerance. What counts as progress is not just, we did a quantum thing. It's, we did a quantum thing that improves the path to logical qubits. Now, one promising direction in photonics is error-resistant encodings, like GKP-style approaches. The idea is to encode information in a way that has built-in resilience, so you're not starting from scratch with every error. Some groups have reported milestones in that direction on photonic chips, which is interesting, but the key word is bridge. An encoding milestone is a bridge toward fault tolerance, not a victory lap. So the reality filter here is harsh. Show me logical or encoded qubits with improving logical error rates. Show me the trend line. If the trend line isn't improving, the architecture might be beautiful and doomed. And as a reality check, look at where photons are already winning today. Networking. Metro-scale quantum networking experiments over existing fiber are a real signal that photons are extremely practical carriers of quantum information in the communication sense. That doesn't automatically solve computing, but it tells you the medium isn't fantasy. It's the computing overhead that's on trial. Chapter 4: The Scoreboard That Ends the Argument. So here's the scoreboard. This is what photonic quantum chips have to prove for a real win. First, loss budgets you can actually read. Waveguide loss, coupling loss, switching loss, detector efficiency, source quality, and how it all rolls up end to end. Second, sources that behave. Single-photon sources that are high purity, low noise, and ideally closer to deterministic behavior, not sometimes a photon, sometimes a surprise. Third, detectors that don't ruin the party. High efficiency, low dark counts, stable operation, and integration that scales. Fourth, fault-tolerant primitives. Not just entanglement, not just interference. Primitives that plug into a real error correction pathway with transparent accounting for overhead. Fifth, encoded or logical performance that trends in the right direction. Not, we achieved a record once, I mean repeatable improvements. A curve you can extrapolate without hallucinating. Sixth, manufacturable modules. If the thesis is foundry leverage, then show yields, packaging progress, testing throughput, and repeatability. Seventh, system-level stability. Because at scale, your enemy becomes drift, calibration overhead, timing jitter, and the 1,000 tiny ways complex systems fall apart. And now the update rules. If you hear, "We're winning the race," discount it. If you see, "Here are the loss numbers, here's the overhead model, here's the encoded performance trend," update hard. And even if photonic quantum takes longer than people hope, silicon photonics still matters, because optical interconnects are becoming core infrastructure for modern compute. So the weird twist is, photonics wins either way. The only question is whether it wins as quantum computing or as the plumbing that feeds AI and everything else. Final standalone line: hype is cheap. Loss budgets are expensive. Subscribe to join the expedition.